What specific problem does the proposed method aim to solve in the context of visual spatial reasoning and maze navigation, and how does it differentiate itself from existing vision language models?
The proposed method aims to solve the problem of teaching visual spatial reasoning to standard large language models, LLMs, specifically for maze navigation, addressing their limitations in genuine visual reasoning and sequential decision-making. Unlike existing vision language models, VLMs, which excel at pattern recognition but struggle with deeper spatial inference, our approach combines supervised fine-tuning, SFT, and group relative policy optimization, GRPO, to enhance the LLM's ability to predict movement commands based on a tokenized visual representation of a maze. This two-stage training framework allows the model to learn step-by-step movement strategies, fostering emergent reasoning behaviors such as chain of thought and self-correction during navigation. Additionally, we introduce MazeBench, a benchmark designed to rigorously evaluate the model's maze-solving accuracy and reasoning sophistication, further differentiating our method from traditional VLMs that do not focus on such structured spatial tasks. Overall, our approach leverages the inherent reasoning capabilities of LLMs, adapting them to process and reason about visual spatial information in a novel way.
How does the proposed method work? Illustrate the process step by step, detailing both the supervised fine-tuning, SFT, and the group relative policy optimization, GRPO, stages.
The proposed method for enhancing visual spatial reasoning in large language models, LLMs, consists of two main stages: supervised fine-tuning, SFT, and group relative policy optimization, GRPO. 1. Supervised fine-tuning, SFT. In this initial stage, the LLM is trained on a curated dataset of 500,000 synthetically generated mazes, each paired with annotated step-by-step solutions represented as movement tokens, e.g., less than up greater than, less than down greater than. The model learns to predict the next movement token based on the maze input and the preceding tokens, effectively acquiring the foundational skill of sequential reasoning for maze navigation. 2. Group Relative Policy Optimization, GRPO. Following SFT, the model undergoes further training using GRPO, which employs a designed reward function to refine its maze-solving capabilities. This reward function includes components for correctness, integrity of movement tokens, and proper reasoning formatting. GRPO encourages the model to develop more sophisticated reasoning by rewarding valid movements and penalizing invalid steps, leading to emergent chain-of-thought behaviors and self-correction during navigation. Together, these stages enable the LLM to effectively learn and improve its ability to navigate mazes through a structured, step-by-step reasoning process.
Can you provide a simple yet illustrative example demonstrating how the tokenized visual maze representation is used by the model to navigate from an origin to a target? Walk through the main algorithm steps, explaining with an example.
The tokenized visual maze representation allows the model to interpret the maze structure and navigate from an origin to a target through a systematic approach. For instance, consider a simple 5x5 maze where the origin is at less than 0 to 0 greater than, and the target is at less than 4 to 4 greater than. The maze is represented using tokens that indicate walls and empty spaces, such as less than no underscore wall greater than for open paths, and less than up underscore wall greater than for walls. In the first step, the model processes the tokenized input, which encodes the maze layout, and predicts the first movement token based on the current position and the surrounding walls. For example, if the model sees that moving down from less than 0 to 0 greater than to less than 1 to 0 greater than is valid, i.e. less than no underscore wall greater than, it might output less than down greater than. Subsequently, the model continues to predict the next movement token by considering its current position and the updated maze representation after each move. This process repeats, with the model generating a sequence of movement tokens, e.g., less than down greater than, less than down greater than, less than right greater than, less than right greater than, etc., until it reaches the target at less than 4 to 4 greater than. The entire navigation process is guided by the learned step-by-step reasoning from the supervised fine-tuning, SFT phase, enhanced by the Group Relative Policy Optimization, GRPO, stage, which refines the model's decision-making through a reward system that incentivizes correct and efficient movements.
What are the theoretical and practical benefits of using this two-stage training framework, SFT and GRPO, compared to traditional maze-solving approaches or models?
The two-stage training framework combining supervised fine-tuning, SFT, and group relative policy optimization, GRPO, offers significant theoretical and practical benefits over traditional maze-solving approaches. Theoretically, this framework enhances the model's ability to perform step-by-step reasoning, as evidenced by the emergence of chain-of-thought patterns and self-correction during navigation, which are not typically present in conventional models that rely solely on direct prediction methods. Practically, the SFT phase equips the model with foundational skills to process tokenized visual maze inputs and predict movement tokens, achieving an initial accuracy of 86% on MazeBench. The subsequent GRPO stage refines this capability further, improving accuracy to 93% and encouraging more deliberate movement strategies through a carefully designed reward function. This dual approach not only leverages the inherent reasoning capabilities of LLMs, but also adapts them to effectively handle complex spatial tasks, demonstrating a marked improvement in performance compared to traditional maze-solving algorithms that lack such nuanced reasoning capabilities.
How was the effectiveness of the method validated in the paper, particularly regarding the MazeBench benchmark? What specific metrics were used to assess the model's performance?
The effectiveness of the method was validated through rigorous evaluation on the MazeBench benchmark, which consists of 100 maze-solving challenges designed to assess the spatial reasoning and planning capabilities of large language models, LLMs. The primary metric used to assess the model's performance was the success rate, defined as the percentage of mazes solved correctly. The results indicated that the baseline model, which utilized direct path prediction without explicit reasoning, achieved 0% accuracy, while the supervised fine-tuning SFT model reached 86.0% accuracy. Further enhancement through group relative policy optimization, GRPO, led to a significant improvement, with the SFT plus GRPO model achieving 93.0% accuracy after 1,600 training steps. This progression in accuracy highlights the model's ability to learn and apply step-by-step reasoning effectively in maze navigation tasks.
What key results were achieved with the proposed method on the MazeBench benchmark, and how do these compare to baseline models? What do these results imply about the model's reasoning capabilities?
The proposed method, which combines supervised fine-tuning, SFT, and group relative policy optimization, GRPO, achieved a notable accuracy of 93% on the MazeBench benchmark after 1,600 training steps. In contrast, the baseline model trained for direct path prediction without explicit reasoning achieved 0% accuracy, while the SFT-only model reached 86% accuracy, demonstrating the effectiveness of SFT in learning step-by-step maze navigation. The significant improvement from 86% to 93% with the addition of GRPO indicates that this method not only refines the model's policy, but also enhances its reasoning capabilities, allowing for emergent chain-of-thought reasoning and self-correction during navigation. These results imply that the model is capable of more sophisticated reasoning processes, as evidenced by its ability to consider spatial relationships and wall constraints at each step, which were not present in the baseline models. Overall, the findings suggest that the proposed training framework effectively equips the model with robust visual maze-solving skills, highlighting the importance of specialized training in enhancing reasoning capabilities in LLMs.